Hi, everyone. What we have here is an example, a simple example of a belt drive with two positions, one on this end, one on this end. The handle here represents the motor, but I thought it's best if you can operate it by hand. Then you get a real appreciation for any resistance, and you get a feedback into your hand as to any binding or whatnot. So go over the basic construction of this and some of the important points that need to be identified. But the main idea of this is to talk about this point right here. This is called the belt tensioner, and we'll get back to that in a minute. But so what I have is I have the main structure, right? This bracketry right here. You can see I've taken the sheet material and I've doubled that because I wanted this to be a little bit more robust because there is going to be tension on this belt, and I didn't want um, these 2 points, the ends here where the axles are, to deflect. If that happens, essentially what happens is this, right? You have two shafts that are no longer parallel. The parallelism of these two shafts is very important to the success of this build. So that's why I went with something a little more robust here. So then I have my axials. This is a spacer that's just acting as a filler right here for where the two bearing flanges are in the plate. So basically, that makes that like a solid mass, right? It acts as a spacer to keep these two surfaces right here parallel also. Some standoffs that are the same size. These two pieces of hex right here. Again, that just added support to keep these spaced properly. And lastly, I have a small axle that my torsion spring, you can see that spring right under here, the torsion spring sits on. So, if you choose to go with a belt drive, which is really cool because you can have your motor at a different location and operate something, further away, it's a great way to use space. But you'll have to incorporate a tensioner. And what a tensioner does is it's in its name, right? It puts tension on the belt so that there's no slack. If there was slack and you were to operate this, the belt would flex. And what that would do is every time, let's say I turn this clockwise, um, there's a pull going on right here. So all the tension is in this. And this would rotate a certain amount of degrees before that tension would be taken up, allowing this one to spin. That's actually called machine timing. It's based on 360 degrees. You're probably not going to experience that, but if you'd like to know more about it, you can address that with me and I'll let you know about it. So, what we do is we add this tensioner to take up that slack. And all that is a little arm that I made up that has an idler in it. You can see the idler right here, right? An idler is just a wheel that is more for routing and guiding of the belt. And you can see down inside here that spring. And you can see that the spring's force is always pushing on that belt. So as this belt stretches, as it could for sure, um, that spring will take up any of that slack and it'll make for a smooth operation of that. Um, an example of torsion springs, you can see that right in there. An example of a torsion spring, for instance, would be something in a mouse trap, for instance, or even a clothespin for hanging clothes out to dry. That uses a torsion spring. So they're pretty common. Um, Old technology, it's just spring steel wound into a diameter that when you take, I got one here that's loose and not bent, you take that spring material and you wind it around a mandrel, that would be the ID of that spring, and you end up with two legs like this. And as I bring these legs together, it's constantly wanting to go back where it came from, right? So there's the spring force. So what I did with this one was I brought these like this. So now that tensioner is constantly pushing on the belt. So that's kind of a cool thing. Belt drives, interesting, kind of fun. You need to have a little bit of precision in your build, and that's these shafts right here, these parallel shafts. The distance is important because that's going to be based on what the belt length is. Another advantage of having the tensioner, or what necessitates the need for a tensioner, is the belts will be cataloged as, let's say, 24 inches long total, but there's a tolerance built into that. It could be slightly larger than 24, slightly smaller, so you never really know how much slack that belt's going to have until you actually build your design. So there it is, belt drive with some of the standard engineering practices, right? Shaft collars holding my axle assembly on. One other little thing here, my belt is only 1/4 of an inch wide. That's the belts we have. If you look at our timing pulleys, this is kind of how they come. You'll see that they're significantly more wide than 1/4 of an inch. What I did was I machined mine down on a lathe so that the flange of the timing pulley would act as a guide also, and I wouldn't have my belt wandering on me like that. So that's very simple to do. It's just on the lathe. And so there it is. Both ends are the same. The only difference would be the shaft is slightly longer and it has a hand crank on it. But again, this will be available in video and on the bench for you to play around with, and hopefully you see something within this design that maybe you could apply to yours, whether it's the torsion springs or just how I put the axle assembly together. So hopefully that helps.